We're going to look at logarithms and more specifically properties of logarithms. These properties are really, really important in terms of simplifying expressions that have logarithms in them. They're also important to solving equations, and for those of you going into calculus, they show up a lot in a calculus course. So as we get started here, I'm going to start with the three most important properties, and those are the sum, difference, and power properties. First of all, these are familiar, hopefully. As I take a look at the sum property, it's similar to, I'm just going to write it, how about over here? So a to the x times a to the y is equal to, if I were to multiply these together, the exponent turns out to be the sum. So this would be a to the x plus y. If I were to do a difference, let's do that in a different color. So if I were to do a difference, that would show up from a to the x divided by a to the y. That would be as an exponent, x minus y. And then finally for the power, and I'll do that one in red. So for the power, that would be a power of a power. So a to the x all to the n. We end up multiplying those two powers together, and this would be a to the x times n. So we're going to go ahead and use these basic exponential properties to get to the properties for the logarithms. I am not going to derive them, but it's just nice to see where they come from. So let's go ahead and grab my blue pen again and start with the sum property. So if I have some log base b, and I've got a product on the inside, so I'm going to use m times n. I can rewrite this as the sum of logarithms. Remember, a logarithm is equal to a power or an exponent. So the sum, when I say the sum of logarithms, I really am talking about the sum of the powers. So this would be log base b m plus log base b n. And then for the difference, that would come from a quotient. So log base b of m divided by n, this is log base b m minus log base b n, the difference of logarithms or the difference of exponents. And then finally, that power of a power rule. So I would write that one as log base b of m to the n. The logarithm represents a power and the n represents a power. Really, this rule just comes down to multiplying powers together, but really bringing the n out in front. N times log base b of m. You really want to know all of these, have them memorized. Like I said, for those of you especially going on into calculus, these do show up a lot. Let's go ahead and simplify using some properties. So here we have a difference of logarithms. Well, I know that difference comes from a quotient. So I want to go ahead and rewrite this. The logs have to match. So I can condense this into a single logarithm, 12 divided by 6. So this simplifies all the way down to log base b of 2. So log base b of 2. Okay, next we've got a sum. So those sums can be condensed into a single logarithm by multiplying what's on the inside. So this would be 10x to the 6th times x to the 9th. So log 5 of, I can just put those two together, 6 plus 9 is 15. So this would be 10x to the 15th. So log base 5 of 10x to the 15th. Okay, next. So for this one, we have a difference. So that would come from a quotient. So I'm going to condense this into a single logarithm, log base 5, 4x over x to the 7th. Now I'm going to go ahead and work my logarithms, or not my logarithms, my exponents on the inside here. As I work those, I can simplify just a little bit. I can cancel 1x, and that leaves me with 6 here. So this simplifies to log base 5 of 4 over x. Lots of different ways you could write that and simplify it, but that's as far as we need to go for these. Okay, number 2. So for number 2, we want to find the values for a, b, and c, as indicated. So we're going to simplify this as much as we can. And I need to start when I'm simplifying with that fraction bar. So that fraction bar really becomes my quotient. And I can rewrite this as a difference of logarithms. So log of the top, x to the fourth, y to the 17th, minus log of z to the 7th. Inside of the first logarithm, I've got a multiplication. So before I do anything with the powers, I've got one more, and that's going to be a sum of logarithms for that one. So that first one expands into two logarithms, log x to the fourth plus log y to the 17th minus log z. Now I wanted it in this form, just log x by itself, log y by itself, log z by itself. So what I don't want are these powers. My other rule, this was a 7 here. My other rule says that I can bring those powers out in front. So as I rewrite this, I'm going to put it right here, equals 4 log x plus 17 log y minus, and that was a 7 log z. So to solve this, we've got our values of a, b, and c. A is 4, B is 17, and C is -7. Okay, see how I did that? So I'm really trying to expand this to the point where I've got log x isolated, log y isolated, and log z isolated. Let's go ahead and tackle part B. In part B, there is not a quotient, but I do see a multiplication, and that's right here. So I'm going to change this into a sum of logarithms. So as I start expanding this using my properties, I get log 3, it's x to the 16th, plus log base 3 of the cube root of y to the 5th. I'm actually really close to this form, right? I want log x by itself and log y by itself. I have a 16 that I can pull out in front, and that's going to simplify the first logarithm as far as I can go. For the second logarithm, I've got a power 5, but I've also got that root 3. I'm going to rewrite this. The cube root of y to the 5th can be rewritten using rational exponents, a fraction, 5 over 3. So let's go ahead and rewrite that as we go here. So for the first logarithm, I am going to bring the 16 out in front. Log base 3 of x plus, before I bring this power out in front, let's just write it as y to the 5/3. Now I'm ready to bring that 5/3 out in front, and I have 16 log base 3 of x plus 5/3 log base 3 of y. And that gives me a, which is 16, because I've got that log isolated. And then I have, let's see, I've got the log of y isolated as well. So that tells me that b is 5/3. Okay, so that's expanding. We can also use a change of base formula. Our calculator is fairly limiting because the calculator only has the common logarithm and the natural logarithm. So there's the common logarithm, and here's the natural logarithm base e. So it only has those two that we can put into the calculator. But we do have a change of base formula that we can use to get around that. So to do our change of base formula, it is like this. So we can say log base b of a is equal to, and I want to change it into a base that's easy to use, like the common logarithm or the natural logarithm. So I'm going to write it in terms of both. So you can either do log a over log b, or you can write this in terms of the natural log, ln a over ln b. I remember this formula because a is above b in the original logarithm, and when I rewrite this using a different base, a is still above b. We're going to use that as we go into these examples, but I do want to start with just a nice kind of simple example before we get there. Let me do this example in red. Let's say that I wanted to calculate log base 3 of 7. In my calculator, I can't do that. There's not a log base 3 key, but I could change this into a common logarithm instead. So I could think of this instead, 7 is above the 3, so that would be the log of 7 over the log of 3. So in my calculator, I can do log 7, you want to close that parenthesis, divided by log 3. And this gives me my answer 1.77. And I can verify it, right? Because it's 3 to what power? So this would say 3 to the 1.7712433749. You don't need all those decimal places, but it should be really close to 7. And it is really, really close to 7. So that's the power that we need. So change of base formula, very powerful. And it's going to really help as we're working through an example like this one. So when I'm solving this, I really want to undo what's happened to the x. So for part A of number 2, I see my x here and here. It's trapped there as an exponent. So I want to apply a logarithm to be able to solve. I'm just going to apply one of my favorite logarithms, one that's on the calculator, to both sides of this equation. So let's go ahead and apply the common logarithm. It doesn't really matter. So we're going to do log of 10 times 1.12 to the x is equal to, I'm going to apply it to the other side as well, 12 times 1.05 to the x. Okay, so my original equation has just been changed by applying the common logarithm on either side. You could also have used the natural logarithm. That would work great as well. Now I'm going to use my properties. I notice that there's a multiplication here and a multiplication here. That's going to become a sum of logarithms. So continuing with this, this becomes log 10 plus log 1.12 times x. I'm going to be able to bring that x out in front. Equals, on the other side, same thing, log 12 plus log 1.05 to the x. Let's go ahead and bring those x's out in front. So they're going to go here and here. And I get log 10. Can we just change that to a 1? 10 to what power equals 10? Let's just change that to a 1. Plus x log 1.12 is equal to, log 12 doesn't simplify. I don't like to use decimals until the very, very end because there's a lot of rounding errors that can happen. X log 1.05. Now remember, your goal is to solve for x. So let's go ahead and locate where our x terms are. Here's an x term and here's an x term. I want all of my x terms on the same side of the equation. So I'm going to move this one over to this side. And I'm going to move the log 12 to the other side as well. A little more room to write? Not much, but I'm almost done. So moving everything around a little bit. So I'm going to have my numbers on this side. 1 minus log 12 is equal to, then I have my two x terms on the other side. X log 1.05 minus x log 1.122. My x is here. I need to isolate the x, so I'm going to factor it out in front, and I'm going to write it actually just down below here. So I'm just going to factor that out in front. So this is still 1 minus log 12 equals, factor the x out in front. So that's going to be log 1.05 minus log 1.12. You're keeping your eye on the prize, right? Because we're pretty much there. This is my x. All I need to do is to divide this guy off to get to my answer. So I've got to divide by log 1.05 minus log 1.12. And I've got to do the same thing on this side. So we're going to divide by log 1.05 minus log 1.12. I'll rewrite it, don't worry, because that's a big mess. Let me rewrite it in blue here. So x is equal to, what's this big mess right here? 1 minus log 12, all divided by, parentheses, log 1.05 minus log 1.12. Let's go ahead and put that into our calculator so we can get a decimal approximation here. So you could put everything in decimal form earlier, but so many rounding errors. I really want to make sure you guys get the right answers the first time rather than having to type it in a bunch of times. I'm typing in what's in blue there. So 1 minus, and I chose the natural or the common log, sorry, so I can just type everything in. Log of 12, close the log, close the numerator, divided by, parentheses for my denominator, log 1.05. Let's, 1.05, whoops. There we go. 1.05, let's go ahead and close that parenthesis. And then minus log, not log, oh, shoot. Okay, I'll do it again. Parenthesis, 1 minus, parenthesis, 1 minus log, what am I doing? Oh, I know what I'm doing. Okay. I'm on my computer keyboard, so sometimes it just doesn't translate quite well. 1 minus log 12. There we go. Close the parenthesis. Close the numerator. Divided by parenthesis for your denominator. Here's where I was going wrong. Log of 1.05. I'm going to close this logarithm. Minus log 1.12. Close the logarithm, close the denominator, equals 2.8, and we want 4 decimal places. So 2.8250. So let's go ahead and write our answer right here. So x is equal to 2.8250. How could you check that? Well, you could plug it in for x. And it's actually easier than you would think, right? So it's totally worth it to check it here. So 10. So I want 10 times, so parentheses, 1.12 to the, you could just use answer here, or you could go arrow up and grab that number and then hit enter, and it puts it right up there as your power. So nice. Parentheses, equals, okay, 13.7733. Let's make sure the other side is equal to this too. 12 times 1.05. I want that power. Let's say that you couldn't arrow up. You're going to use your answer key, which is right down here next to enter. So you're going to do second. Oh, and you want the answer from up above. Second answer, not that one. So instead, let's clear this, and then we'll just type it in. I forgot it wasn't our last answer. 825003635. It probably won't be perfectly equal, but it's really, oh my gosh, it's really, really close and pretty much there. So we're feeling good about that. So just by checking it in our original equation, we can make sure that we've got the right answer. Okay, that was part A. Now for part B. Part B is actually much easier. Part A was a tricky one to start with. For part B, I can go ahead and use my definition of a logarithm. So 2 is my base, 5 is my power. So this says 2 to the 5th. So it says 2 to the 5th is equal to 7x plus 5. Well, I can go ahead and do 2 to the 5th here, or you might even know what 2 to the 5th is, and we end up with 32. So 32 is equal to 7x plus 5. Subtract a 5 from both sides. That's what, 27 equals 7x. Divide both sides by 7. So much easier. X is 27 divided by 7. 27 divided by 7. So 3.857, it said 4 decimal places, right? So x is about 3.8571. We could check this and we would need to change a base, but to check it a little more easily, you might just do the exponential form there. We need 2 to the 5th, so how about this form of it? We need 32 to equal 7x plus 5. So I'm going to do 7 times x, so 7 times the answer that we got. I'm going to do second answer this time, so second answer done by the enter key, plus 5. And sure enough, it's 32. So feeling good about that answer. Okay, next one, part C. So for part C, I noticed that I've got a plus sign. And that plus sign means that I can combine these into the logarithm of a product. So I'm going to rewrite this as the log of x times x plus 4 equals 4. Let me just simplify that a little bit. If I distribute my x, I get x squared plus 4x is equal to 4. This is base 10, so I can go ahead and rewrite it using exponential form. 10 to the 4 is equal to x squared plus 4x. 10 to the 4 has 4 zeros. 1, 2, 3, 4. So that's 10,000 equals x squared plus 4x. If I subtract the 10,000 from both sides, 0 is equal to x squared plus 4x minus 10,000. Now, I doubt there's two numbers that multiply together that have a difference of 4. So I'm going to use the quadratic formula, of course. So we've got some good review going on here. So the quadratic formula. So x is equal to the opposite of b, so negative 4, plus or minus the square root of b squared, 16, minus 4, times a times c, so times 1, times negative 10,000. All divided by 2a, which is 2. So inside my radical, I've got 16 plus 40,000. So I have 40,016. Ooh, that might be a perfect square, huh? Let's take the square root. So second square root, I'm going to grab that answer. But it's not, and that's okay, because we're just approximating these. So x is equal to negative 4 plus or minus 200.0. Let me rewrite that. Okay, let me rewrite it. Perfect. Okay, so x is equal to negative 4 plus or minus 200.039996, keeping a bunch of decimal places here until I'm ready to round. And I've got two answers here. So I've got negative 4 plus 200.031236, all divided by 2. And I have the same thing, but with a minus on the inside, divided by 2. Let's go ahead and put that into the calculator. So parentheses, negative 4, use the little negative net next to the enter, negative 4 plus, and you can just grab this answer here and then hit enter, parentheses divided by 2. So there's that one. I want to use this same input, but I want to subtract instead. So you can either arrow up to grab that one and then hit enter. If your calculator doesn't do that, you can do second entry. So I'm going to do second and then enter key. And that brings up that last calculation. I want to just change this guy to a minus, plus to a minus. And this gives me the other answer. So I've got my two answers. I'm going to go ahead and put them over here. So x is equal to 98.019998, or negative 102.019998. If we were to put the negative in, we would see that it was actually undefined. So logarithms Cannot use negative inputs. So that's the graph of a logarithmic function. So that means I've got to throw that out. Logarithms have restricted domains. You could always check it by attempting to type it in. If you did log of negative, I'm just going to round it to 102 just for checking purposes here, plus 3. So if you were to attempt to check this to make sure that you can get one on the other side, you immediately end up with a non-real answer. So this is the correct answer. Okay. Oh, did I put that into the wrong one? Because this got so long. Second quit. This would actually be, for this guy, I'd actually have to put it in here, right? So even simpler, I wouldn't do the plus 3. So that was my mistake there. So this is, I wouldn't do the plus 3. Delete, delete. And I'm actually just going into, since this got so long, I started writing over the next one. I'm just going into this equation right here. This is part C. So if I tried negative 102 into log of x, I end up again with a non-real answer. So let me go ahead and just quit here. And I'm going to go ahead and write my answer, the only answer right here, and I'm going to do it in purple. So for this one right here, x is approximately 98.019998. If we wanted to round that to 4 decimal places, 1, 2, 3, 4. I'd have to round this. I can't round 9 up to 9, so I'd have to round 199 up to 200. So this becomes 98.0200. Okay. Geesh, that one got long. What do I have? 2 left? Okay, 2 left. Normally I would not do this, but because I was writing so big, I really need to just start erasing some of this stuff. So let's go ahead and just erase. You can grab a separate piece of paper here, but I want to make sure I've got enough room to work this next one. So we're watching for negatives. We're following those properties really carefully. In this one, I've got a negative sign in the middle. Whoops. So I've got a negative sign in the middle. That one's going to change into a quotient. So I can start by rewriting this. So this is going to be log of x plus 3 is in the numerator. X plus 1 is in the denominator equals 1. This is the common logarithm, so I can rewrite it using exponential form. 10 to the first equals x plus 3 over x plus 1. That's just 10. Let's go ahead and cross multiply. 10 x plus 1 equals x plus 3. Distribute that 10. 10x plus 10 equals x plus 3. Let's move the x's so that they're together. And I'm going to do the same thing with the numbers so that they're on the other side as well. So I get 9x is equal to 3 minus 10, which is negative 7. So x is negative 7/9. Remember, we couldn't have a negative sign, but when I put my negative into the inputs here, let's go ahead and double check it. So I'm going to do log parentheses negative 7/9 plus 3 minus log negative 7/9 plus 1. And we're hoping that this comes up really, really close to 1. Oh, and it gave me a syntax error. What did I do wrong? I'm going to hit go to. My syntax error, I used the wrong negative sign. So I want to grab the correct negative, which is next to enter. I know better. Let me go over here. This is going to be incorrect as well. Negative sign. Okay, now enter. And there, I got my 1. So even though this guy was a negative number, it didn't make x plus 3 negative or x plus 1 negative. So I'm okay to keep that as an answer. And I can go ahead and write my answer in purple here. I'm just going to transfer it over. X is negative 7/9. We've got just one more. So the last one here has a couple of natural logs in it, and I notice on the left side There's a plus sign here, so that means that I can change this into a single natural log with a multiplication. So ln of x times x minus 5 equals ln of 3x. I can multiply this through, so the natural log of x squared, let's go ahead and simplify this as we go, and let's not write it in yellow. Let's do it in blue. So we get the natural log of x squared minus 5x is equal to the natural log of 3x. I can't just rework this using exponential form, but I do notice that whatever's been done to one side has also been done to the other. So that means that these two arguments need to be the same. If they both have the same operator on the outside, what's inside needs to be the same. So I can really just more simply write that x squared minus 5x needs to equal 3x. Let's go ahead and move the 3x to the other side, and we can use a zero property to solve this. X squared minus 8x is equal to 0. I can factor the x out. X minus 8 equals 0. This gives me two possible answers. X is equal to either 0 or positive 8. As I try and put 0 in, I'm going to end up with a non-real answer, but we can go ahead and try it. So the natural log of 0, let's see. The natural log of 0, which is my x, plus the natural log of x minus 5, so that would be 0 minus 5, and hit enter, and that gives me domain. So 0 doesn't work, but I can go ahead and try it with 8. I've got my input here. Let's just go ahead and grab it. If you can't grab it and hit enter, go ahead and do second and then the enter key. So second enter. And I'm just going to change both of those zeros to an 8. 8. I get 3.178, no longer get an error. And let's go ahead and put it on the other side as well. So I want to make sure that it's equal to the natural log of 3 times x. So in my calculator, that's going to be the natural log of 3 times 8. And I end up with the same answer. So I'm feeling really good about that. I need to get rid of 0. 0 does not work in my natural log, but 8 does. So x is equal to 8.